Okay, let's get started then. Hi everyone, I'm Sanjiban Choudhury. I'm an assistant professor at Cornell. I lead the Portal group. And today I'll talk a little bit about the connection, an obvious connection between motion prediction and model-based RL. My talk today will posit that many of the old paradigms that we have had for forecasting in general was built on shaky foundations. And this has led to a plethora of problem over the last decade or so that we've been working on forecasting. And I know, many of the people in this room or organizers of this workshop have worked on fixing these problems. But I think as a community, we all should really be thinking about this problem as one of model-based reinforcement learning. Um, Model-based reinforcement learning not only offers a principal fix to many of the problems we have observed in forecasting, but it also leads to a much needed unification in our field. And we can stop talking about motion prediction and just talk about models in general. That's my dream. Okay, sounds good. So I'm going to talk about there are actually two motivating applications that kind of influence my group's work in motion prediction. One of them is collaborative cooking, where you have a team of humans and robots doing collaborative tasks together. Cooking is just a delicious example of that task. The other is the application of self-driving that many of us have worked on and where there's been a plethora of prediction work. And what do these two disparate applications have in common? It turns out that both of them really care about predicting human motion around robots well. So, last time I was here in this workshop 2 years ago, I talked a lot about our self-driving efforts. Today, I'll be talking about my group's work on collaborative manipulation with cooking as an application. It's a much more newer area where there's newer opportunities, newer challenges. So it should be fun to dive into this a little bit. Okay, so here's a brief look at our system. For assistive and interactive cooking, we call the system Mosaic. In the system, we have a human that is communicating with two robots using natural interactions like languages and gestures. So typically, the human asks the robot to help them with a recipe. You have, a fixed base manipulator doing tabletop tasks like stirring a pot. You have a mobile manipulator fetching condiments. What's cool about this application is that there's a bunch of machine learning algorithms that are running on both robots. The robots are sensing the human's motion through cameras, overhead and onboard cameras. And as you'll see, very naturally responding to the human coming into the workspace. So these robots are working in a very interpretable and legible way around humans. And so, we've extensively tested the system, done several end-to-end trials, and I'll talk a little bit about there's a lot of things going on underneath the hood, but I'll focus mostly on the prediction aspect of this problem. So one of the things we learned while trying to get this system up and running is that predicting human motion is essential for collaborative cooking. So, perhaps it's obvious, but if you have robots that are not responsive to humans when they are coming very close to the robots, it can be really discomforting for humans, right? Imagine Neha here trying to put some vegetables in the pot and the robot's just stirring around her. It's kind of uncomfortable for her. On the other hand, it's much more natural when the robot anticipates when a human is about to come into their workspace and kind of makes room for the robot. Okay, good. So how did we make this work? So what's happening is there's an overhead camera that's looking at the human. We're using media pipe to extract a human skeleton off the camera and then using our prediction models underneath the hood to predict human motion. Whenever the robot predicts that the human's about to come into their workspace, they make room for the human. Prediction here is essential because if we just use the current pose, the safety margins are too small for comfort. So prediction here makes a world of difference. The way we make prediction work is we look at the current image of the human. We then extract a 2D pose, project that 2D pose into 3D coordinates, run a forecaster to predict the human future motion, and then use that forecaster to plan with in the MPC of the robot. Okay, cool. So that's the overview of our motion prediction system. Let's try to look at this task of motion prediction as a machine learning problem. And whenever we look at any problem, we as machine learning problem, we ask three fundamental questions of ML. What is the data? What is the model? And what is the loss? So I'm going to start with, before I go into the details, almost all of the work that I present here is done by my amazing student, Kushal Kedia. He'll be presenting our work at a poster of this workshop today at 2:30 p.m., but he's all over ICRA, so he has a conference talk tomorrow, as well as spotlight spotlight talks at other workshops. So we'll definitely catch him to learn details about things that I'm talking about today. All right. So so three fundamental questions of machine learning. What's the data? What's the model? What's the loss? Let's start with the model. Okay, so let's start by thinking very simply about the problem. What's our goal? Our goal is to predict human motion around robots. Like in this case, we would like to predict that the human here is going to safely reach for the pepper and not go and collide with the robot on. Right? Sounds very simple. So we are going to think of a very naive model. This naive model is going to take as input the current context, right? You can put in whatever you want in the context, but imagine the current snapshot of the scene, as well as the history of past human motions, and use this to predict the future human motion, okay? So it's a very simple sequence to sequence mapping problem that we want to solve. Nowadays, this is very easy to do with transformers. So you feed as input to the transformer a sequence of human states, as well as the context, and decode and predict the human future, right? Easy peasy, very standard machine learning pipeline. Of course, we're going to run into a problem. And the overall problem is that human motion really depends on the robot action. Okay, so what do we mean by this? Let's take a look at the scene I showed you before, okay, where you have a human and a robot in front of a cabinet with items in the cabinet. There's actually one of two possible futures that can happen, that can play out here. Future one is that the robot goes to grab for the tartar sauce and the human grabs the pepper, right? Future two is the robot grabs the pepper and the human has to wait, okay? These are two possible things. There are more things that can play out, but let's take these two possible things. Now, the naive model that I showed you before will actually average over these two possible futures because the model ignores the dependency on the robot action. So, it's seeing the same input and two different outputs. It's going to average over these two outputs, and very bad things are going to happen as a result that we'll see shortly. Okay, so this is one of the first challenges we ran into. And our key insight here was what the human does depends on what the robot will do. And we need to capture these dependencies explicitly in our model when we are training these motion prediction models. So we can improve our naive model to have a much better model where we take as input, as before, the context, the human history. We can also add in the robot history, but crucially, we also want to add in the robot's goal, because the robot's goal tells us which mode we are likely to be in. And using all of this, we want to predict the human future. Okay, so we want to train a model that's conditioned on the robot's goal to be more predictive. Okay, so that's a better model. And once we started writing this model, we realized, hang on a minute, this API looks awfully similar as a dynamics model in an MDP. So can we start to view motion prediction more formally as a model-based RL algorithm? So we're going to create this bridge between motion prediction and model-based RL. So to recap, in model-based RL, we are trying to train a transition model in an MDP that takes as input a state and an action and predicts the next state, right? So we are training this model M hat that's predicting ST plus 1 condition on ST and AT. Now, in our particular example of human motion prediction, the state ST happens to be the context, as well as the human history and robot history. We can think of all of this as kind of representing the state of the system. We can choose an action representation as the goal the robot's trying to get to. You can use any different action representation, like the plan of the robot, but we found the goal to be a very convenient action representation. And as a result, your output happens to be the human future, the future human poses. Okay, so we can make this bridge between motion prediction and MBRL using these state and action definitions. All right, why build this bridge? Well, there's a lot of wisdom in MBRL that we can start importing to human motion prediction. And one of my favorite wisdom from working in MBRL is that, what makes a model good? What makes a motion prediction model good? Is it all about accurately predicting the world? No, that's impossible to predict how the real world will evolve. It's impossible to predict how humans would move. I mean, the entropy of that distribution is massive. Instead, a good model, so a good model need not accurately approximate the real world, but a good model is one such that if you plan with the model, we get a good policy. That's the wisdom of model-based reinforcement learning. I'm biased, but I think model-based reinforcement learning answers all the questions we could have about forecasting. So in terms of the model-based RL tells us we should be predicting the next state conditioned on the robot action. Easy peasy. As far as the data, we'll see that the model-based MBRL says we shouldn't be training on off-policy data. We should be training on off-policy and on-policy data. And we've known this result for 10 years now, or maybe 12 years now. And the last thing is the loss function that we look at. Model-based RL says we shouldn't be trying to exactly predict the real world, but instead we should be training on a value-aware loss. And this is a very recent ICML paper that we published in the last year. Okay, but let's not get ahead of ourselves. Let's start with the model. So the paper that we are presenting at the conference is called ICRA. It's called Interact, where we talk about how we train a human motion prediction model conditioned on robot actions. So we already talked about this before. We would like our model to condition on both the robot history as well as the robot goal. Turns out this is really easy to do with sequence models like transformers by basically using masked attention. So you feed as input your human history and robot history. You condition on the robot goal. So this is a future state that the robot's trying to get to. And then you predict the human future, right? And such models have been more recently been used also in self-driving. So there's a lot of precedence for such models. Okay, so let's take a look at how this conditioning makes a difference in this example of picking items off of a cabinet. So I'm going to show you a plot. Here, the plot is showing you error across time. The red curve is the marginal prediction or the naive model that does not condition on robot actions. The blue curve is Interact. This is our method that is a conditional model that conditions on the robot action. And you can see that there's a band where the difference between these two predictions become very big. So what's happening at this timestamp? So this is the critical timestamp where both the robot and the human are about to reach for the objects, right? So this is a timestamp we really care about. And we see that the marginal errors should almost nearly double the interact errors. So when we take a closer look at the marginal prediction is that the marginal prediction is averaging over both modes. So it's not clear, but what you can see is that it predicts that the human is not going to, its result get by averaging over kind of the human is sort of halfway through their motion. Whereas if you do action condition prediction, you get a very accurate prediction that the human is in fact reaching for the object, right? And so this is very important because the robot should, if the robot wants to reach for the object without colliding with the human, it needs to know that the human's also reaching for the object in this context. Whereas the marginal prediction wouldn't give you that output, and you might result in a very unsafe behavior. Okay, so to summarize, it's really the lesson we learned when we designed our model is that we should be designing models that condition on the robot action rather than training unconditioned models. All right, so that was model. Now let's move on to data. What does MBRL have to say about data? Just like we did before, we can think of the naive thing to do when it comes to data, which is the common machine. If you want to train a machine learning model, go find the largest data set out there, train your model on that data set. We started by doing just that. Looked at all the various motion prediction data sets out there, like AMAS, UMU Panoptic, Human 3.6 million M, and there are many more coming out. And all of these have various kinds of human interaction data that we can leverage to train our models. And so a naive idea might be take this human-human data and train your model on this human-human data. Into a problem when you try to do this, which is the gist of the problem is that the human-human data, which you use at train time, is going to be fundamentally mismatched with human-robot data that you use at test time. That's going to be the problem. So we can sort of dissect this problem into two sub-problems. Both of these are a problem of mismatches. The first problem is one of embodiment mismatch. So perhaps it's obvious, but human and robot embodiments are very different. And it's not trivial to take models trained on human data and just transfer it to models that we're going to use when we interact with robots. So that's one big problem. The second is a distribution mismatch problem. So the off-policy distributions that your model sees at train time is going to look very different from the on-policy distributions it sees at test time. So problem one is more of an artifact of this application, and I'll talk a bit about how we do it. While problem two, I think, is a deeper, more pervasive problem that's true for many applications. So let's start with problem one, which is the embodiment mismatch problem. So in a nutshell, the embodiment mismatch is as follows. If we train a model that's on embeddings that we get from human-human data, the API doesn't quite work when we want to transfer to human robot. I mean, let's say, for example, the number of joints in the human hand is going to be different from a human robot. And not just the number of joints, the way a human moves is different from a robot. So all of these differences are going to cause a significant degradation in performance. How do we fix this issue? Key to solving this mismatch is to create some sort of pairing between human-human and human-robot data points. And so what if we try to pair these two data points, right? Now, unfortunately, when we started doing this work, we found that there was really no good human-robot data sets out there, period. So one of the first things we had to do is we had to create our own small data set of human-robot interaction. So this data set is called the collaborative manipulation data set. It's a data set of both human-human and human robots together doing tasks. These are over 5 tasks. We have both high quality motion capture data for all our tasks, as well as video data for each of these tasks. They are 5 household tasks with over 4 hours of motion for the human-human interaction and over 1 hour of motion for human-robot data. And the nice thing is this data is paired. So for every human-human task, there's a human-robot task as well. And that's actually key to helping us do this transfer. So I encourage you to go check out our data. It's all there, all on GitHub at this link. If you have any issues, please send us an email. We're actively supporting this data set and adding to it. Okay, so our key idea here was to generate these equivalent human-robot states. And there's a lot of work that went into try to figure out this equivalence that I won't go into details now. I mean, there's lots of literature out there on how to align human and robot data. So, but we found a very simple and clever way of doing it using motion capture and tracking. So the key thing is once we have a data set of equivalent human and robot states, we can train embedding functions that pull together aligned human and robot data, right? So now these embeddings are the ones that are then used by the transformer. So by aligning human and robot data, this allows for effective transfer from human to robot. Okay. So the overall picture is that you want a model that you pre-train on human-human data and that you fine-tune on human-robot data, but you have to do the alignment for the fine-tuning to actually work. That's sort of the approach that we went with. All right. So that's one problem of embodiment mismatch. There's a second problem, which is that of distribution mismatch, which is a mismatch between your training distribution and your test distribution. So what do I mean by that? Let's forget about the human to robot transfer for a second and just look at how human robot data looks at train time and test time. So at train time, we have the robot being teleoperated by another human, right? So the other human is able to move the robot in an optimal way, just like an expert would like. But at test time, the robot is planning with our learned model, and it can make a lot of mistakes. It can do strange motions at test time. So there's going to be a mismatch between distributions at train and test time because of this. And as a result, the model that you learn at train time can be way too optimistic. It can think life is wonderful and great. You know, the human's going to move perfectly. Doesn't know how a human will react to strange on-policy robot motions. And so once again, MBRL answers all of these questions. So one of the key things that MBRL says is that when you train your model, you shouldn't be training only on off-policy data. You should also be training on on-policy data. And the mathematically right way to do this is to train on 50% off-policy and 50% on-policy. So in other words, if we were to look at a standard MBRL off-policy loss, it says you should fit the model only on states and actions visited by the expert policy. We do not want to do this. Instead, what we want to do is we want an interactive MBRL loss where we train the model on 50% data sampled from your expert and 50% data sampled from your learner. And this is an old result that Ross and Bagnell proved back in ICML in 2012. And so we have a clear recipe for how we should be training our models. And so this leads to a final framework of how we should be collecting data. Should pre-train on human-human data, train on 50% off-policy human-robot data, and train in an aggregate, train also on 50% on-policy human-robot data that we aggregate. So as the model becomes better and the policy changes, we want to keep aggregating data and train on both of these buffers. Okay, I know we are coming up to the end, so I'm going to skip to the end. So we've experimented with this setup on a number of different users and tasks. across some of the various tasks that I showed for on the COMAT data set. I'm going to show you just one of the results. So we're going to look at how these forecasting errors compare. Let's begin first by looking at the robot data only across 3 different tasks, plus all of the data set. So this is, the red shows, what if we trained a model only on robot data? Orange shows, what if we trained a marginal model, right? And surprisingly, you see the errors come down because the robot data only has very small data, whereas a marginal model is able to leverage all of human data. So even though it's not quite doing the right thing, it's burning down the error because of the sample complexity benefits. And then our approach further improves on the marginal model because it's able to condition on the robot action. And so one observation is that if you only use human-robot data, you have worse performances because of the lack of data, but conditioning on robot actions is more accurate than marginal prediction. So that's the end of data. We should be training on 50-50 off policy and on policy. I'm going to skip over the loss, but maybe give you a very high-level picture. So nominally, when we think of the loss, we try to match the L2 loss between the ground truth and predictions. But one problem is that the L2 loss treats all errors as equal. Which is definitely not the case when we do human-robot interactions. For example, if you look at this plot of human-robot interaction, we see that precisely at areas where the human and robot are coming, where the 2 humans are coming in close proximity, we have extremely high errors in these critical states, because and these are states that we care more than other states, right? These are states where we want to get our prediction better. One of the key insights from MBRL is we shouldn't be training on L2 loss that treats all data points equally, but instead we should be training on a value-aware loss. So instead of training on a total variation loss or an L2 loss, train on a loss that cares about the value or the cost induced by the forecast. So I'm going to skip this. Go right to the end. Okay. So we made a connection between MBRL and motion prediction, and we imported a lot of the wisdom from MBRL into motion prediction. So in summary, for data, you should be training on 50-50 off policy and on policy. Models, you should be conditioning on robot action and loss. You should not be using L2 loss, but upweight losses that correspond to higher planning cost. I want to thank my group portal, as well as a number of collaborators for the results we showed today. And I want to end by saying that this is a really exciting area, because by making these connections, we are able to sort of leverage a lot of the active research going on in model-based RL and kind of bring them over into human motion prediction. And so these are some of the threads that we are very excited about and working on. And with that, I'd like to thank the organizers once again. And yeah, thank you.
Thank you so much. Thank you so much. Envías or okay.
Okay, one moment.
Are there any questions?
Hello, can you hear us? Can you hear me?
Yes.
Yes.
We have a bit of an echo, but do we have any questions? Okay.
Hey Sanjay, I have a question for you. Thanks a lot for your interesting talk. So you gave us an indication that datasets should be 50% coming from expert and 50% from learned policy. What instead any indication about the quality, right? You tell us how to split those data sets according to this ICM paper of 2012, but do you have any insights about the quality or any particular study on this?
Yeah, that's an excellent question. So I'll say two things. One thing that makes um, forecasting or prediction very different from imitation learning is that suboptimal data is a good thing, because or data where the humans behave in strange ways is a good thing because it helps make your model better. So that's one thing I would say. In terms of I think the key thing is you need coverage of data. That's sort of the key insight from that old ICML paper. And the 50-50 thing tells you that you want models that are both covering good states. So they're covering the kind of states an expert would visit, but then models that are also covering bad states that the learner might visit, right? And you want to sort of not forget either of these experiences. And so the 50-50 actually comes clearly from the performance difference lemma. So that's there's a very strong theoretical connection. So that's the first comment. The second thing I would say is that there is some interesting work on noise and making your model robust to noise in your sensors. So when we did our work for this mosaic work that I showed, we actually had to inject noise into the history explicitly to make it robust to sensor noise. And there's been relatively less work on this, but I think this would be a very interesting thing to analyze and connect with the kind of domain randomization results we see from computer vision, bring that over into the motion prediction domain. Yeah, but great question. Thank you.
Yeah, thanks a lot.
Thank you.
Yeah, we thank the speaker again. Yeah, sorry for these technical issues. That's quite challenging today.
Yeah.
See you next time.
All right, see you.